the way that we isolate that logarithm is the same way that we would solve an equation like 3y minus 6 equals 9, right? We see that outside that logarithm, there is multiplication by 3 and there's subtraction of 6. So we need to add 6 to both sides and divide by 3 to get the logarithm by itself. So that's our first step. And then the second step is just to rewrite as an exponential equation. So just like we did on Monday, when we were going back and forth between exponential equations and logarithmic equations. So we'll solve this one in a sec, but let's start with something a little simpler. So if I have log base 5 of x plus 1 equals 2, so the logarithm is already isolated because there are no operations outside of the logarithmic expression. So I have log base something of something, and then there's nothing else going on that side of the equation. So I can jump right to step 2 and rewrite that as an exponential equation. So log base 5 of x plus 1 equals 2 says that if I raise my base to the second power, I get x plus 1. So my base is 5. If I raise 5 to the second power, I get x plus 1. And remember, we know that because we know the logarithm is equal to the exponent. So we put what the logarithm is equal to onto our base, and that's equal to the input of the log. And well, we know what 5 squared is, yeah? It's just 25. So 25 equals x plus 1. And so x equals 24. Now, one thing we do have to think about with logarithms is extraneous solutions, because remember when we solved rational equations, we had to check our final answer against our restricted values, because there are restrictions on the domain of rational functions, which means we could end up with a solution that doesn't actually work in the original equation. And the same thing was true with when we solve radical equations. Because there's a restriction on the domain of a square root function, we had to check our answers back in the original equation to make sure that we didn't end up with some negative stuff that was going to mess it all up. The same is true with logarithms. Remember that the domain of the logarithmic function is only positive numbers, so we can only take a logarithm of a positive number, which means if I end up with a solution here, I just have to check it back in the input of my logarithm in the original equation and make sure that that's positive. So if I put 24 into x plus 1, I get positive 25, and that's positive, so it's okay. So if I were to plug my answer back in and x plus 1 ended up being a negative number or 0, that would not be a valid solution because I can't take the logarithm of a negative number or 0. So we always have to check for those extraneous solutions. So our last step in solving is to solve the resulting equation, which will either be a quadratic equation or a linear equation, and then check that the solution doesn't make the input of the log in the original equation negative or 0, i.e. check for extraneous solutions. So let's do a few more. Let's do that one that I just erased. So if I can remember it now. So let's do 3 log base 5, this is different but basically the same, of x minus 2 minus 6 equals 9. So the first step is to isolate the logarithm. So that is this whole entire thing. So I need to add 6 to both sides. So we get 3 log base 5 of x minus 2 equals 15. And then I'm going to divide both sides by 3. There's another way we could do this. We could use our log rules and say this is the same, so that coefficient can become the exponent on the input of our log and say that's equal to 15. But I don't know about you, but I'm not really interested in multiplying x minus 2 by itself 3 times. So because this is an equation and we can do operations on both sides, we might as well do whatever makes it work out simpler. So whereas we could use our log rule to bring that 3 up, I'm not going to, because it's a lot simpler to just divide 15 by 3 than to multiply x minus 2 by itself 3 times. You would end up eventually with the same answer. We're just doing it the easy way because we can. So we'll go log base 5 of x minus 2 equals 5. And so now we're ready to write this in exponential form. So we're just saying that, okay, if you take my base, which is 5, and you raise it to the exponent, which is 5, that should give you x minus 2. I do not know off the top of my head what 5 to the 5th power, nor do I want to figure it out in my head. So anybody, it is a really big number. It's quite large. 3125. I mean, that's not that big. 3,125. Could be worse. Equals x minus 2. And then to solve for x, we just add 2 to both sides. So 3,127. And then the last step is just to make sure that that solution doesn't make the input of our logarithm negative or 0. And 3,127 minus 2 for sure is not less than 0, so we're good. Does this make pretty good sense? What's nice is that, as you may have noticed, like we keep learning how to solve different types of equations, but really most of them were just like undoing something which turns the equation into either a linear or a quadratic, right? Like when we have rational equations, we clear fractions and we end up with a linear or quadratic equation. When we have radical equations, we undo the radical and get a linear or a quadratic. So basically kind of all these special circumstances, we just have to rework the equation into a linear or a quadratic, and then we know how to solve. So the same is true with logarithms, is we just rewrite it in that exponential form, and then all of a sudden it's not a log equation anymore. It's just linear or quadratic. So let's do a couple more. Let's solve log base 2 of x plus 3 equals 4 minus log base 2 of x minus 3. So in order to rewrite a logarithmic equation in exponential form, we need 2 things. One is that we have to only have a logarithm on one side. We can't have logarithms on both sides. because otherwise that would be saying, like, we'd have to like say that the logarithm was like part of the exponent. That would be annoying. So we need the logarithms all on one side, so I'm just going to add log base 2 of x minus 3 to both sides. So as you work with these guys, you can treat this whole thing like a single number, so like as like one value. So just like if I had like 4 minus x, I would add x to both sides to get that x over on the other side. The same is true of like that whole chunk. So you kind of want to think of a logarithm like that whole expression as just like a single value. So we have log base 2 of x plus 3, and then plus log base 2 of x minus 3 equals 4. So now I only have logarithms on one side, but I still can't write this in exponential form because I don't have a single logarithm, right? Because when we have a logarithmic equation, we can say, okay, if I have a logarithm equal to a number, then that's the same as my base raised to that number equals the input of my logarithm. But if we have two logarithms, then like, what's the base and what's the single exponent, right? We can't write a single exponential expression when we have more than one logarithm. So that's where what we did yesterday, the condensing and expanding, comes into play. So like you will likely, I mean, unless you're reviewing it, other than in this class, you will never have a question that's just like expand this logarithm or condense this logarithm, like just for the heck of it. It's not something we just do for fun. It's something that we do in the context of other problems because it allows us to simplify or solve or do whatever it is that we're trying to do with that expression or equation. So like this is the type of thing where, or a type of problem where that would come up, is I see that I have two logarithms, they're added together, and so if I were to condense the left side into a single logarithm, that would allow me to rewrite this equation in exponential form. So anytime you have a logarithmic equation and you can condense one side into a single logarithm, that's the route you want to take. So I have addition here. The coefficients of both those logarithms are 1, and so I don't have to worry about bringing up any exponents. And then it's addition, and so I can rewrite this as log base 2 of x plus 3 times x minus 3. And again, keep those log rules just like 2 inches from your eyes until the test, like for all the problems we do, so that you can keep looking back at them and not for a second have to wonder like, oh my gosh, is that addition or is it multiplication or is it subtraction, or can I break this up or can I put this together? It's so easy to like go down a road where you're like making up log rules that aren't actually valid. So just keep those in front of you so you can keep referring back to them and internalize those log rules correctly. So equals 4. So now everything we just did was like step 1 of solving our log equation. It's our first goal is just to get a single logarithm on one side of the equation. And once we do that, we can rewrite this in exponential form. So my base is 2. The logarithm is equal to the exponent. So 2 raised to the 4th power is going to give me the input of my log. So x plus 3 times x minus 3. So we'll simplify the left side. That's just 16. And then we're going to distribute on the right because I see that this is going to be a quadratic equation because I'm going to get an x squared, which means my goal is to get 0 on one side. And I can't get 0 on one side. Like I could subtract the 16, but I can't get 0 unless I can combine like terms over there, right? If we have a bunch of stuff in parentheses, we're not going to be able to combine like terms. So I want to get rid of those parentheses. It gives me x squared minus 9 because I get negative 3x plus 3x for my two middle terms. So that just adds to 0. And then there's 2 routes I could take for solving this. We could subtract 16 from both sides to get 0 on one side, which is typically what I do for any quadratic equation. And then I see that x squared minus 25 is factorable. So we would go x plus 5 times x minus 5. I usually recommend that you solve by factoring if you can, only because the route where we take the square root of both sides, a lot of people forget the plus or minus, especially on tests. It's easy to forget little things like that. Whereas if you factor, you get both the positive and the negative 5 just by setting both equal to 0. So we get x equals 5 and negative 5. But you could also, from here, if you notice that there is no like x term, so there's no middle term, you can isolate x squared by adding 9 to both sides and get x squared equals 25, and then take the square root of both sides. You just got to remember that plus or minus. In this particular problem, we end up getting rid of the negative anyway, which we'll do in a sec. So if you forgot it, you'd get the right answer, but I'd also notice that you forgot it and that you got the right answer because you made a mistake that turned out nicely in your favor. In this situation, we'll get rid of that negative 5 because if I take negative 5 and I plug it into the inputs, or I guess I should go to the very original equation, the inputs in my original equation, notice that plugging negative 5 in for x makes both of those inputs negative. So negative 5 plus 3 is a negative 2, negative 5 minus 3 is a negative 8. So that's not a valid solution because I can't take the logarithm of a negative number. So this guy goes away. And it's not necessarily because the solution is negative, it's because when I plug it in to the input of my logarithm, it makes that negative. So I could have a positive down here. Like if I'd ended up with like a positive 2, that also wouldn't be valid because 2 minus 3 is negative 1. So don't fall into the trap of like, oh, I got a negative number, it must be wrong. Like you actually have to plug it into that input. And then if we take our positive 5, 5 plus 3 is positive 8, 5 minus 3 is positive 2, so that is a valid solution because it makes both my inputs, or the input of both my logarithms positive. So this is my final answer. Does that make sense? And let's do one more. So the variable in a logarithmic equation can really be any piece of it. So I always think of like logarithms as having 3 pieces. There's like the base, there's the input, and then there's like what it's equal to, which is the exponent. And any of those can be your unknown. So we can also solve equations like, where'd it go? Log base x of 4. Oh, I have a 3 right there. 3 times log base x of 4 is 1. I don't like where I put that x. It doesn't look like subscript-y enough for me. So in this one, our unknown is actually the base. But the approach we're going to take is exactly the same. And this particular equation, there's a couple routes we can take, and it's just one of those things is as you get more comfortable with it, you'll kind of get used to like what is easier for you. So we can isolate that logarithm. So this is my logarithm. And we can isolate it by dividing both sides by 3. So we get log base x of 4 equals 1/3. Which means that x raised to the 1/3 power is equal to 4. What is x to the 1/3? What is that the same as? Oh, don't make that I don't know. This is a mystery face at me. You guys know this. Yes, it's the cube root of x, right? Fractional exponents are the same as radicals. So this is the cube root of x. You guys know so much more than you think you do. Gotta know you know it. So then I would solve this by just cubing both sides. So raising both sides to the 3rd power. 64, yes, you're very close. So to the third power is equal to 4 to the third power, which is 64. So we get x equals 64. And in this case, we don't have to worry about checking that for extraneous solutions because the input of our logarithm is positive. And unless we set up an equation that just flat out like was impossible from the beginning, you're not going to end up with like a negative down here because you can't have a negative base for a logarithm. But the setup of the equation would make that fairly obvious from the beginning that it just wouldn't work because there's no negative number that we can raise to any power to get a positive number.
You only check it if the answer is if there's a negative answer.
No, it's the reason I'm not checking is because the input of my logarithm has to be positive, and in this case, the input of my logarithm is a constant. It's 4, so my unknown isn't part of the input. So I'm not worried about plugging my solution in and making it so I have the log of a negative because it's always the log of 4 here. Okay. It's just the base that is my unknown. So one thing that, again, as you get more comfortable working with these and working with log rules and things like that, you'll start to notice these things a little bit more. But one thing that I notice when I see this problem is like the fact that we got a fraction on the right side made it kind of annoying because we wondered for a minute what it meant to have x to the 1/3 power. And you can avoid that in this case. Remember on the last problem here, I was like, I don't want to figure out what x minus 2 to the 3rd power is. Like, that is no fun. But on this one, if you used your log rules and said this is log base x of 4 to the 3rd, and that gives me log base x of 64 equals 1, then that's saying that if I take my base, which is x, and I raise it to the 1st power, I get 64, which all of a sudden is a lot easier to solve than the alternative. So the reason if I got this equation from the beginning, I would probably decide to solve it that second way. And what I would notice in the original equation is that dividing by that 3 gives me a fraction, whereas bringing the coefficient up as my exponent will give me an equation that doesn't have any fraction in it. And so that's why I would decide to go the second route rather than the first, is because I'd noticed that my exponent was going to be a fraction, and that doesn't seem all that great. Whereas back here, bringing my 3 up just gives me a huge polynomial that I don't really want to deal with. And so it's just a matter of working with these enough that you notice which one is going to be a more efficient way to solve. Neither one is wrong in either case. It's just that one can often be more efficient than the other. And so x to the 1st, of course, is 64, and that's your solution. Not too bad. These are fun, right? Now that you guys feel super comfortable with them and they're easy as pie, they're wicked fun. Don't you think? They're like puzzles. I love puzzles. Okay, so we're going to spend the rest of the time just working on your homework for tomorrow. You don't have any online homework. It's just a worksheet. And I want you to work on it in class mostly because the first few problems, I really want to make sure you're practicing without a calculator so you can think through them. Make sure you read the instructions because, as you've noticed, there are a lot of different things we can do with logarithms, and none of them are more right or more wrong, except in the context that if you're not following the instructions, it would be wrong, right? So if it tells you to condense it, you don't want to expand it. If it tells you to expand, you don't want to condense. So in particular, the first few problems are just rewriting the equation. You don't have to do any simplifying or solving on the first